All right, so the recorder has started. What we'll do today is to take a look at a few algorithms, and we'll take a look at the time complexity of those particular algorithms. Um, I'm supposed to talk about the master theorem, which I have slides prepared in the past, but I think it's probably better to focus on just these few categories as concrete examples, because you might have learned these algorithms in some of your other classes already. So this is not going to be a completely new topic, but the way we analyze the time complexity is going to be that's going to be the focus of today's class. All right, so we'll start with linear search. And you probably already know that linear search, if the time complexity is T of n, then it is an element of big theta of n. All right, so here's a big, quick quiz, which doesn't count for any points. What is big theta? What does it mean when I say something is an element of big theta of n? Okay, so first of all, how is big theta defined? Something is in big theta if and only if there. Yep.
It's the upper bound.
It is not just the upper bound, it is both the upper bound and the lower bound. So if it's just the upper bound, it is big O, which is actually big omicron, which is also a Greek letter, but we just say big O most of the time. If it's a lower bound, it is big omega. So if it is in both, then it is big theta. So in this case, the T of n, which is the actual amount of time that a particular linear search algorithm or implementation of linear search, um, that T of n is an element of big theta of n, which means n is a tight bound of T of n. Does that make sense? Okay. I think this is pretty intuitive, but the question is, how do we prove it? So the way we prove it is to look at the time complexity, and we're going to look at linear search as a recursive linear search. So this is not the linear search that you're used to, because you're used to linear search being a loop, right? You're having a while loop that says as long as the index is less than the size of the array and a bracket I does not equal to the key that you're looking for, stay in the loop and increment the index by 1 in the body of the loop. That's a typical way of implementing linear search. This is also linear search. It is recursive. Now, do you really want to implement linear search as a recursive algorithm? No. But for the analysis of the time complexity, this is actually convenient. Okay? So we'll take a look at this algorithm first. This is my way of representing an algorithm. And I borrowed this notation from when I was teaching CISP440. I have not taught CISP440 for a long time. Well, basically, it's kind of the same deal. You have the name of the subroutine being lin search for linear search, and then we have all of these parameters. So A is a parameter that is passed by reference. B is passed by value, and so is V, which is also passed by value. The type of A is it is just an array of some kind of value type. I don't even care what value type we're dealing with here, as long as we can check whether something is does equal or not. And then V is the value that we are searching for in the array, which is of the same type as the array. In other words, I just want to know, is this value V in the array of A? That is basically what this is asking for. Now, why do we need B? Because B is the starting point. It B is for beginning. So B is where do we want to start in the array in our search for value B. So that's why B is here. Are we doing okay so far with the three parameters of this subroutine? We got the array. We got which index is the first one that I need to start to search for, and then we also got V, which is what we are trying to look for. So the return type is Boolean. We just need to say, yes, we found it, or no, we did not find it. And there's a local variable R for result. So the result is initialized to 0. And then what we do here is we just want to there's only one single conditional statement. The conditional statement says, as long as b is less than bar a bar, which means b is still a valid index into the array, because the first element has the index of 0, the last element has the index of bar a bar minus 1. Bar a bar is my concise way of saying the length of the array. Okay, so I borrowed that notation from the discussion of tuples because I also use the same notation when we talked about how many items are in a tuple. So bar a bar is basically the length of the array. So this is a guard condition. So the guard condition is guarding the actual statement here. Colon equal to is a old assignment operator that I borrow from Pascal, which is a really, really old programming language. So I'm just making sure this doesn't beat me. So now let's take a look at this expression here. The first part of the expression says, a bracket b equals to v. So that means, hey, we just found it. Okay, the index b, is indexing into an element of a that has the same value as what I'm looking for. Or, okay, so here's an or, which means if the element at index b is not what I'm looking for, well, then we have a second chance of making the disjunction true. So in this case, we have a recursive call. And when you look at the recursive call, it has the same array A. It has the same value that we are looking for. But where we start looking is b plus 1 now. So it does the same thing as a typical iterative linear search, except it is done by recursion. So are we understanding the algorithm and understanding how it works? So if I were to write this in C, regular C, I can do this in one single line using the ternary operator. But since I'm not writing in C, this is kind of a long way of doing exactly the same thing. All right, so if we don't have any questions about this, then we'll look at the overhead of every single statement. I'm going to assume the calling of a subroutine is constant time. In other words, just the overhead of pushing all the uh, arguments on the stack, pushing the return address on the stack, and popping all of those things from the stack. It just takes constant time per invocation. Then we take a look at line 7. Line 7 is just a initialization of R. I think it's fairly safe to say that this is going to take constant time. Is that okay? All right. And this one here is comparing B against the number of items in the array. I'm going to assume this is also going to take constant time, which sometimes it is and sometimes it is not. It depends on the implementation of quote unquote what we know as an array. If it's a linked list, this can take longer, okay? Because we might have to traverse all the way throughout the linked list to find the last element, in which case it's going to be, big O of n by itself. But I'm going to make the assumption that this is just a constant time operation. Is that okay? Any questions at this point? Okay. And this part here, I think we can assume this is also constant time. Okay. And once again, if the array is actually a linked list, this is not going to be constant time. But assuming that we are indeed using a typical array, this is still constant time. So the only thing that is not constant time is going to be lin search, the recursive call of lin search. But in the recursive call of lin search, the number of elements that the next call is responsible to deal with is going to be one less than what I was told to deal with. Does that make sense? Because the start index is no longer b, it is now b plus 1. Is that okay? All right. So that means that I can change the way we express the time complexity to something like this. Okay, let me just kind of point out here where we are looking at here. So T of n, which is the actual amount of time that it takes to solve a problem with size n, is going to be some kind of constant k1. That's combining the initialization of R, the comparison against the length of the array, and so on. That's just a single constant time. And we're going to add the amount of time to solve a subproblem, which is 1 less than my original problem, t of n minus 1. So are we associating the time complexity, which is this part here, with the algorithm that I just described? We good? Okay. All right. So in this case, it would have a time complexity of just n. Now, how do we prove that? In other words, I gave you a recursive definition, right? So with any type of recursive definition, it has to stop at some point. And in this case, when do we stop? What is the case where we can end the recursion? The recursion ends when b equals to bar a bar. Does that make sense? Okay, because b is increasing, with every embedded recursive call. At some point, it's going to get to bar a bar. In which case, we will say, b is no longer less than bar a bar, so the default value of r, which is false, is returned. Yeah. Is that okay? So we'll call t of 0, because in that case we have 0 elements left. So we'll call t of 0 some constant. And the question is, if t of 0 is just some constant, making that assumption, how do we make sure that t of n is going to be some kind of constant times t of 0? So what proof technique do you think is going to be useful in this case? You have a recursive definition. We know the base case is t of 0 being some kind of constant. So what would be the proof technique that we should use in order to prove that t of n is an element of big theta of n? Proof by induction. Very good. So it's going to be proof by induction that we could use here. I'm not going to show you the proof in this case because it's actually kind of trivial. So I'm reserving the time to do a more complicated proof for a slightly more complicated case. Is that okay? All right. So we're moving on to the next class of algorithms, and it will be the not so efficient sorting algorithms. In this case, I'm just going to be picking on selection sort. So we'll first take a look at the algorithm. Let me fit the entire algorithm in on the screen and just kind of explain what are the parameters and what it is doing. So we are passing by reference A as an array. So this is the array that this selection sort is supposed to sort. And then we also have B, which serves kind of the purpose, which is starting at index B, we want to sort that portion of the array. So we are somehow assuming the indexes or the elements corresponding to indexes less than b, they're done already. Okay. So now we take a look at the algorithm itself. If bar a bar minus 1 is greater than b, then we still have something to do. So what does that mean? Bar a bar minus 1 is the index of the last element in the entire array. And if the index of the last element is greater than b, then we still have some portion of the array that we might need to still do some work with. Does that make sense? Okay. So what are we going to do here? We have two local variables. We have m as a local variable, and we also have I as a local variable. M is initialized to b, I is initialized to b plus 1. And I can tell you what M is trying to represent. M is trying to represent the index of the largest element of the array starting with B, index B. So if you look at the entire array, B is somewhere in the middle, and M is the index of the largest element starting with index B all the way to the end of the array. I'm just trying to find the largest element from index B. I, on the other hand, is an index that I use in the loop here because I need to scan through the rest of the array to find the largest element. Is that okay? I could initialize I to just B as well, but it would be pointless because the same element cannot be greater than itself. So I can pretty much guarantee that I can start with b plus 1 instead of just b. The loop itself is just a regular while loop. It says here while I is less than bar a bar, which means as long as I is a valid index into the array, then I go ahead and compare a bracket I versus a bracket m. If a bracket I, which is the element that I'm scanning, is less than a bracket m, then m gets I. So m is trying to remember the smallest index of the smallest, not the largest. Sorry, I mentioned largest earlier. It is actually the index of the smallest element, starting from index b. And then after this, I increment I by 1 so that I can look at the next element. So this loop here from line 7, which is the initialization, all the way up to line 14, is really just trying to find the index of the smallest. I misspoke earlier to be the largest, but it's trying to find the smallest element starting from index b and all the way to the end of the array. Is that okay? I mean, that's typically what you need to do with selection sort, is to find the index of the smallest or the largest, depending on which way you want to sort the array. And then it's going to swap a bracket b with a bracket m. A bracket b is what is taking the place that the element a bracket m should be at. Okay, so swapping is just going like that. And then after that, I perform a recursive call. So this is once again a recursive call by calling a selection sort again, but this time the starting point is b plus 1 instead of b. So basically, the first invocation is only responsible to get the smallest element of the entire array to a bracket 0. The next invocation, which is recursive, is responsible to find the second smallest element and get it to a bracket 1, and so on. Is that okay? All right. So now we look at the time complexity. So the time complexity is going to look like this. Okay, so the reasoning is up here. Let's assume T of n denotes the time required to sort an array of n items. I did not really phrase this correctly. I should have said an array with n items to be sorted, because your starting point can be anywhere. So n is describing how many elements starting with index b that we have to sort. Does that make any sense? Okay, all right. And then we know that T of 1 is k for some constant k. Well, let's check out why we know that that's just a constant time when T of 1 is being considered. So when T of 1 is considered, then we only have one element left. And when there's only one element left, then bar a bar minus 1 is greater than b is going to be false. And as a result, we skip around this entire thing because we have nothing to do. Why is that the case? Because if you have sorted everything except for one element in the array, by the pigeonhole principle, or modified version of the pigeonhole principle, we know that whatever element is left is also sorted because everybody else is already at the right place. So the only one thing that we go like, we are not sure whether that's at the right place or not, also has to be at the right place already. Okay. So if that is the case, then what else can we describe? This is because the loop and recursion only occurs when bar a bar minus 1 is greater than b, which is kind of what I just said, which means there are more than one elements to sort when b is less than bar a bar minus 1. So in general, for all n that is greater than 1, T of n can be described as k1 plus k2 times n plus T of n minus 1. Wait, hold on a second here. What is this doing? Okay, so let's check this out and find out what it is doing. So what it is doing is using K1 to describe all the constant time operations. Line 7, constant time. Line 8, constant time. And the rest is not constant time. Okay? So K1 is going to capture the time to initialize M to initialize I, and also to check the condition, which is all the way up here on line 4. So those are the constant time operations. What about K2 times n? So K2 is a coefficient to factor in all the operations that we have to perform n times. So what operations do we have to perform n times? Well, the loop itself, line 9, is going to have to perform n times. Everything inside the loop on line 10, 11, 12, 13, all of those have to perform. Oh, okay, I forgot one thing. The swap operation is also constant time, so that's going to be absorbed into K1. But focusing on K2, it'll be the loop, okay? So someone may say, but Tech, that loop doesn't, well, actually, it does take n iterations because we have to find the smallest element. So we have to scan and look at every single one except for the first one. So technically, it's n minus 1, but it's easy to bump it up to n because we can just kind of nudge K1 to absorb one of the original K2. So it doesn't really change the equation all that much when we're dealing with n minus 1. So K2 times n, and then we also have T of n minus 1. T of n minus 1 is accounting for line 15, line 16, which is the recursive call. Because in the recursive call, we have one fewer element to deal with, so the amount of time it's going to take is going to be T of n minus 1. So are we doing okay so far with this generalized equation of T of n is sum K1 plus n times sum K2 times T of n minus 1. Okay? So given this, what can we do about the math part of this? So what we want to do is to get a closed form of T of n. And to get the closed form of T of n, this is the actual solution of T of n is K times n plus 1, the whole thing divided by 2. And the proof can be done by many ways. Proof by induction is one of those. So in the proof by induction, the base case is when n equals to 1. Then T of 1 is K times 1 plus 1, the whole thing divided by 2, which is K. The induction step further states that if we assume the closed form works for case n equals to j is greater than or equal to 1, then it should also work for n equals to j plus 1. Oh, I think I missed one little important key here, which is k can be assumed to be k2. It doesn't all change all that much if k is assumed to be k2. So let me back to. Oh, so the first part of the sentence also says k2 times n is going to be asymptotically dominant with respect to k1, just because one is multiplied by n and the other one is not multiplied in any way. So that helped us to simplify the whole thing to T of n is just K2 of n plus T of n minus 1. So from here, we basically just want to say, if I just make K equal to K2, can we prove this? Now, I think we have seen an equation like this before, except it wasn't expressed like this. Do you guys remember when we saw something similar to this, but it's not exactly the same thing? It was very early in the semester. Well, I wouldn't say really, really early. It's after we talked about functions. Do you guys remember, the two-dimensional thing? How we can map a two-dimensional pixel system into all natural numbers. So the way we figure out the natural number corresponding to the bottom row, has basically something like this in it, except it wasn't expressed like this. It was using the sigma notation, but it boils down to the same thing. But in this case, we can start with a closed form, and we just need to prove it by induction. So this is another chance of looking at proof by induction. So in proof by induction, we have a base case. So in this case, the base case is T of 1 equals to K. And the induction step has two components. The first component is the assumption that the closed form or the theorem is correct when n equals to j. And now we want to prove that the theorem is also correct when n equals to j plus 1. So now we start with t of j plus 1. T of j plus 1 by definition is k of k times j plus 1 plus t of j. This part here comes from this equation because we are changing k2 to just k. So this part is because of this. So are we okay on the first line? How we extend t of j plus 1 to be k times j plus 1 plus t of j. Okay? And then what we do is immediately make use of the induction assumption. So, because the induction assumption says the theorem is true when n equals to j, so that means t of j is assumed to be the same as k times j plus 1, the whole thing divided by 2. So going from the first line to the second line, or the first step to the second step, we are making use of the induction assumption. Is that okay? Do we? All right, okay. So from line 2 to line 3, that's just algebra. So in this case, the algebra is extracting k. We are factoring k out because both components has a k here. And then we multiply j plus 1, the whole thing, by 2, so that we have a common denominator. And then the third step is really just to look at the numerator, and then once again do factoring, because the two components of the numerator, they both have j plus 1 in it. So when you look at what is left over, would be just this j plus this 2. So we end up with j plus 2 times j plus 1, the whole thing divided by 2, and then this whole thing also has to be multiplied by k. But that's exactly the end result that we would like to see when we're trying to compute t of j plus 1. So therefore, we have proven that t of n being k times n plus 1, the whole thing divided by 2, that's the closed form of the time it takes to perform selection sort. Is that okay so far?
Yep. How would you know the proof is wrong? What would the final result be to prove that your proof is wrong, that you can't find it?
Well, we make so this part here, we already started off with the right closed form, and this is just a verification of that is indeed correct. So we already started off with the right closed form. All right. And then what do we do? So what we do next is to take the limits. So we know that we can proceed to show that t of n is an element of big O, or big omicron of n squared, and t of n is also an element of big omega of n squared. So the way we do this is because t of n does not oscillate, it does not switch between two values, so we can now prove both at the same time. So the way we do this proof is we look at the limit of t of n divided by n squared. We know t of n is k times n plus 1, the whole thing divided by 2, and then we want to divide the entire thing by n squared. And we can extract k divided by 2 to be outside of the limit. So now we have a limit of n going to infinity, and we want to find out what happens to n times n plus 1, the whole thing divided by n squared. And that we break it up into n squared plus n. N squared divided by n squared is just 1. N divided by n squared is 1 divided by n. Now, when you have a constant in a limit, we know the answer pretty much already, because when you take the limit when n approaches infinity of 1, then the answer is just 1, because it's a constant. It does not even depend on n. So this part here just becomes k divided by 2. This side here, when n approaches infinity, 1 divided by n, the limit is 0. The whole thing approaches 0. So that means we have a 0 on this side. So we end up with k divided by 2, and that's the answer. All right, so how does that help us? Okay, so we have k divided by 2. Well, So now you have to ask, is k divided by 2 0? No. Is k divided by 2 infinity? No. So that makes it possible for us to determine that t of n is both an element of big omicron of n squared as well as big omega of n squared. We have established we have a tight bound because the ratio between the function that we're trying to approximate and n squared is a constant. The constant turns out to be k divided by 2. All right. So are we doing okay? Are we relating this particular discussion to that other discussion that we had about a week ago, when we talked about big theta, big omega, and then big omicron? Okay. All right. Very good. So that takes care of this particular algorithm. Binary search is interesting also because the time complexity of binary search is big O of log of n, big omicron of log of n. It's actually also a tight bound. So the pattern of the time complexity of time binary search is T of n being k1 plus T of n divided by 2. Okay, so I did not present you with the algorithm. So how do you think it's going to look like as a recursive algorithm? Binary search. We're talking about binary search. It's about that time of the day. And it's also me. All right, so how do we write binary search as a recursive algorithm? The non-recursive algorithm is pretty easy. You have the B. Yeah, go ahead.
You just keep cutting the array of them.
Correct. So you still have to keep track of where you're starting and where you're ending. It depends on which programming language you're using. If you're using a programming language like JavaScript, where you can use the slides to create a shallow copy of an array, you could potentially use it that way. So you basically just make a quote unquote new array for each recursive call. That can be done. But you can also just change the indexes of where is the starting point and where's the ending point of where you can find the value. Okay. So I want to kind of show you the recursive algorithm because I didn't put it into the notes here. So I want to show you the recursive algorithm. And that's not the window I want to use. Maybe this one? Yeah, we can use this one here. All right. So we'll go ahead and take a look at binary search, bsearch.bs.c. There we go. It's going to return a Boolean, but this is straight C, so we do not have a bool type. So we have binary search, and you have to pass a bunch of stuff. Let's just say that we're dealing with an array of integers, okay? So we have the array of integer, const, and array A. You also have to give it unsigned B as the start index of where you think the array may contain the value V. And then you have to give it E, which is the ending point. So B and E are both indexes of elements in the array. One is marking where to begin, and the other one is marking where to end. And obviously, you also have to say what value we are searching for. So V is representing what value we are searching for. And I think that's all we need. All right. So how do we write this function? When I write anything that's recursive, the first thing I think of is, when do we stop? Okay. So tell me when I can stop in a binary search algorithm.
If the value you selected is the value you're searching for.
Okay. But are you sure that there's anything left in the array to even consider? So how do we know the the portion of the array that we need to consider is empty? There's nothing. So that has to do with the relationship between B and E. B is supposed to be the beginning, N is supposed to be the end. Go ahead.
When B is greater than E.
Because B, when when B is greater than E. That is correct. So when B is greater than E, then we go like, there's nothing that we can look at. Okay, so in this case, now I really do not like to use a return inside the conditional statement. So this is typically what I do. There's actually nothing we need to do here, but I can leave behind a comment and say there is no element to consider. Okay, and obviously we have a return result at the end. All right, so the else case is the one where we have at least one element to consider, because when B and E are the same, we still have one single element to consider. It's just that that element is both the beginning and also the end of the range inside the array that we need to consider. Is that okay? Well, this is binary search. So what is the hallmark of binary search? What do? We have a range of an array starting from here, ending here. So what do I need to do next? The midpoint, right? We need to go find the midpoint. So we'll go ahead and say, okay, let's go find the midpoint. It is B plus E, the whole thing divided by 2. Is that okay? Yes. So we are finding the midpoint between the B and the E. And then we'll make a comparison now. Okay, so now we want to say, is this what we're looking for? But I cannot just say, let me see if it equals to. Okay, now we would like this to happen. This would be ideal, because if this happens, I can just kind of go back without any recursive call and just say, yep, we found it. But I would not structure the code like this. Okay, so instead, I would structure the code to look for less than first. All right. So if A bracket M, okay, someplace in the array, is less than K, which is the value that we are searching for already, which one do we need to adjust? Do we need to adjust the beginning or the end? Assuming the array is sorted in an increasing order, or at least non-decreasing. So the array is sorted in a non-decreasing order. A bracket M is known to be less than K, which also implies A bracket M minus 1 is also less than K, A bracket M minus 2 is also less than K, and so on. So do I adjust the beginning or do I adjust the end? So, say again?
And
The beginning. Because the array is sorted in a non-increasing way, so the smallest element is going to be A bracket 0. The largest element is going to be all the way to the other side. So we are actually adjusting the beginning, because everything from A bracket M backward all the way back to A bracket 0, they will all be less than K. In other words, they cannot be K. So that's why we adjust the beginning. So normally, with a loop approach, you would have said something like B equals to M plus 1. But remember, we're trying to do this recursively. So that means, okay, so we are not going to change B, but M plus 1 is still going to be useful. So what we do is we say result is a recursive call of B search. We're still searching in the same array, except B this time is M plus 1. The end has not changed, and the value we are searching for also has not changed. So I'm going to pause here and see if there are any questions about line 14 of this code. We are assuming the array to be sorted in a non-decreasing manner, or if it's easier, you can think of it as increasing order. Are we good so far? All right. And then the next thing we do is to ask else if A bracket M is greater than K. Because if A bracket M is greater than K, that means A bracket M plus 1, which is greater than or equal to A bracket M, is also greater than K. It also means A bracket M plus 2 is also greater than K, and so on. So this time we move the end of the range. So we have to do something about E being the end of the range of the array. Say again?
equal to n minus 1.
Yep. But instead of doing that, I'm just going to do it like this. Oops, m minus 1. There we go. There we go. So here's a quick question. What if I forget this plus 1 or this minus 1 here? What would happen to the algorithm?
Would that live forever?
Potentially, yes. So it depends on the number of elements and how the values are arranged, but you can potentially end up in an infinite loop if you forget the n plus 1, the plus 1 of the n plus 1, or the minus 1 of the m minus 1. So that can potentially happen. So it's really important, this plus 1 and the minus 1, they're really important because if you don't, sometimes it works, it exits even with the right answer, and other times it doesn't do it. Okay. All right. Well, we got another else here, right? I wonder what this else is corresponding to. How can I end up on line 22? If it's less than, we have already got line 14. If it's greater than, we've already got line 19. So by the time we get to line 22, it means they're equal to. I don't even need to check. The fact that I'm on line 22 means we found it, right? So this is the only time when I can say result can be anything non-zero. I'm just using 1 here, and that's it. So this is the recursive version, or one way to write the recursive version of binary search. Are there any questions about binary search in this particular way? If somebody is thinking, but Tag, this is awfully inefficient because we keep passing A and K throughout all the iterations, my answer is yes, it really is pushing all of those things as arguments on the stack for each invocation. There are certain languages that allows you to define a nested function definition within a function definition. Unfortunately, C is not one of those languages. So with those languages, you can define a subroutine within bsearch, and that subroutine that is nested within the definition of bsearch will have access to the local variables as well as all the parameters of the enclosing definition, and they do not need to be passed along anymore because each recursive call would use the same A and the same K anyway. So JavaScript can do it. I'm not sure about Python. Does anyone know whether Python can define nested function definitions? Nobody knows. How is that possible? I know JavaScript can do it. I know Java cannot do it.
Java can't do nested function?
Cannot. As far as I know, you cannot have a definition of function within another definition of a function. Well, first of all, technically,
That's correct.
yeah. Yeah, technically speaking, Java does not even have functions because everything has to be a method. There's no way to define a standalone function that is outside of a class in Java. In C and C++, yes, okay, but in Java you cannot have a function that is not a method. So when we say function in Java, it has to be a method of some kind. It has to belong to a class. It can be a really kind of stupid class and everything is static, but it still has to be a part of a class. All right. So looking at this code here, what about the time complexity analysis? So to do that, what we need to do is to look at, for each invocation of bsearch, which part is quote unquote constant time and which part is not constant time. So we look at this entire code, we look at all the lines, okay? All the lines except for line 14 and line 18 are constant time. Is that okay? So, the initialization of result, constant time, whether B is greater than E, constant time. In the else case, the calculation of M, constant time. Checking whether A bracket M is less than K, constant time. Whether it's greater than K, also constant time. So the only thing that is not constant time would be line 14 and line 18 in the recursive call. So the recursive call, generally speaking, has about 1/2 of the elements, the remaining elements, as the number as n. It's not exact because, I mean, it depends on the rounding, right? Of b plus e divided by 2, because the b plus e can be let me see, can be an even number. If it's an even number, you have the actual midpoint. If it's an odd number, you can end up with two, quote unquote, two midpoints, and we'll just pick one. But we can say that the size of a problem in the recursive call is about 1/2. Okay. So what that brings us is the analysis back to the slide over here. So this is the time complexity of binary search. If the problem given to me has n, not n elements in the array, just n elements within B to E as indexes. Okay, so n is not the size of it's not the size of the array. It is the number of elements for this particular invocation to deal with. So T of n, the time taken to search for a particular value within this range of elements, is K1, which is absorbing all of the constant time stuff that we need to do. We check B versus E, we check the element, greater than, less than, and so on. Those are all absorbed by K1. T of n divided by 2 is the amount of time of the recursive call. Is that okay? So once again, we have a recursive definition. Not only is the algorithm itself recursive, but the time complexity is recursive as well. So with any type of recursive definition, we can now basically say that it's going to be big theta of log of n. And the proof of this, okay, I have to think about that. I mean, intuitively, it makes sense, but the proof is, I know how to reverse it, because if you think about the size of the problem being something 2 to the power of something, you can prove the log thing in reverse, basically. Instead of proving the time complexity T of n is log 2 of n, you can reverse it and say, if the time complexity is n times k1, then the problem size is 2 to the power of that n. So there's a way to prove it. And then we move on to merge sort. So merge sort is also very interesting. How many people still remember what is merge sort? Still remember? Okay. So the question is, how do we know the time complexity of merge sort? So I wrote another module that talks about the time complexity of merge sort. But what I want to do in this case is, what if the actual time function of an algorithm looks like this? It has k1, which is a constant time thing, and it has something that is proportional to n, so k2 times n. And this is the interesting part, is the recursive call. There are two portions of the recursive call, and they don't even have to be even. They don't have to be half and half. We can split it using r as a ratio. So one side is r times n. So r has to be it has to be less than 1, but it has to be greater than or equal to 0.5, because I need to know which side it is lopsided. So r is the one part that is greater than or equal to 0.5. So we divide the problem into two halves. One half is going to be r times n, and then the other half has to be 1 minus r, the whole thing, times n, in order to reconstitute the entire thing. And that's basically what merge sort does, is it splits the problem into quote unquote two halves, and then each half is going to take X amount of time. I believe I believe quicksort is the same way, because it breaks the problem into two halves. The two halves are not necessarily the same size, but we can make an assumption of what that R can be. Is that okay so far? All right. So the informal proof is just looking at an invocation tree. So do you guys know what is an invocation tree, or uh, what I'm trying to represent as an invocation tree? No, yes, maybe, no. Okay. All right. So let's take a look at an invocation tree. It's basically a way to look at how we perform the recursive calls. All right, so let's just say that this is your original problem, and the ratio R versus N, the other way around, 1 minus R is kind of like that. So this is the first call, okay? This is the call, initial call to the subroutine. So it has two recursive call, one recursive call to take this half, and then the other recursive call to take the other half. All right? And the one part that takes this call here is also going to apply the R versus the 1 minus R ratio and break this part up into these two portions. And then the other one will take the smaller portion and proportionally break it up into R versus N minus R. So this is what I mean by a invocation tree. It's just representing each node is representing one particular invocation. If they are along the same branch in the tree, they are recursive. The one is calling the other one, calling the other one, calling the other one. So you can basically kind of imagine this continues on this and versus that, and this is a lot smaller now. So we have only this much left, this versus that, and so on. So this is what I mean by an invocation tree. They all end when the number of elements to process is just one. Is that okay so far? All right. So R doesn't even have to be 0.5, which is kind of ideal because if it's 0.5, then the tree is balanced. When the tree is balanced, it will use the least level of um, layers in order to get the same job done. But even when R is lopsided, we can still perform this proof here. So the formal proof is like this. So we will say that the first layer or the first level has n items. So in this particular picture, we basically mean this part here is n. Okay? So we now break n in the first level of the invocation tree. We break that n into Rn and 1 minus R, the whole thing, times n. So this side here, this is R times n. This part here is 1 minus R times n. Are we good so far? Because this is the nature of merge sort and some of the other algorithms. It breaks it into two parts, and then each part is can be a certain ratio of the original problem. So when you look at this one here, okay, what is the width over here? This will be R squared times n, and then whatever is left over here is going to be R times 1 minus R times n. Does that make sense? One way to look at this is every time we follow the left branch, we're multiplying by R. Every time we follow the right branch, we're multiplying by 1 minus R. Is that okay? All right. So at some point, you're going to look at this tree, and then when you look at the total number of items for each level of this tree, they are the same. So if you add up this much with this much here, you reconstitute the original n. Does that make sense? If you add up these four, okay, there are two here, but I can also just kind of show that there's one here and there's one here. So if you add up everything at the third level of the entire tree, they also add up to just n. How do we know that?
just divide it, it's just n divided.
Just divided, yep. But you can also prove this mathematically. Because with this one here, this is a r, so this one is actually also 1 minus r times n. And then this one here is going to be 1 minus r squared times n. Does that make sense? Okay. But there's something about this, okay, that makes it kind of, I think we have seen this somewhere else. Okay, r squared, r times 1 minus r, 1 minus r times r, which is kind of the same thing. So we got two of these things having the same length. And then this is 1 minus r cubed. So if I give 1 minus r a special name, let's call that q, okay? What are we looking at here? R squared times 2rq times q squared. What do you think we are looking at? Sounds like polynomial-ish kind of thing, right? But this is specifically one type of polynomial that we call, there are two things that we put in the parentheses and then we raise the power of that entire thing. It's a binomial. So every single level is basically the components of a binomial to a certain power. If you look at, not counting n itself, but if you look at the coefficient that we're multiplying by n. Is that making any sense? Okay. So if I say q equals to 1 minus n, just for convenience, okay, the next level is going to have r cubed times r squared cubed, and then we have, so the number of things that we have here, we have seen this somewhere. We have analyzed how many r squared cubed we're going to have, how many r q squared we're going to have, and how many q cubed we're going to have. What is that? I mean, how do we get these coefficients? How do we get to the third level? How do we get these coefficients? It becomes r plus q cubed. And then the next level is r plus q to the power of fourth, and so on. This is the binomial theorem. Okay, we're getting back to the binomial theorem. So that's another way to basically say, oh, okay, so that means if I just add up all the sizes of the subproblems of each level, they all add up back to n. Are we good so far? All right. So if that is the case, okay, that's basically what this particular paragraph is trying to describe, is we are guaranteed to add up to just n items for each level. So the question is, how many levels are we talking about? The number of levels is going to be proportional to 1 divided by r. So that's kind of the quote unquote fan out ratio. It's not going to be exactly 2 unless r is exactly 0.5. So if we are looking basically at this part here. If r is exactly 0.5, then 1 divided by 1/2 is 2. So now we have log n divided by log 2, which is basically log 2 of n. So that's the ideal case because now your tree is even-steven, is balanced, so we have the least number of levels. But what if r is 0.75, okay? Well, if r is 0.75, you would still end up with a number that is greater than 1 when you divide 0.75, when you divide 1 by 0.75. That turns out to be what? 1.3333 and so on, right? So you still have a number that is greater than 1. So that means the log of that thing is also greater than 1. So that means you're still having log n divided by log of something. And as a result, I mean, the bottom line is, this is just a constant. We don't really care what it is. It is the n, which is the number of items for each level, times log n, which is the number of proportional to the number of levels that we end up with. Is that okay? So it shows this is a generalization of the original merge sort time complexity, because in the original merge sort time complexity, R is basically 0.5. You're guaranteed to, let me think here. The number of runs is guaranteed to be divided by 1/2. Right, so it's guaranteed to be in merge sort, R is guaranteed to be 0.5. So that's why we also know that you only need log 2 of n runs of the split merge algorithms in order to completely sort an array. So are we doing okay at this point? Do you guys still remember how merge sort works? Do you want me to kind of demonstrate merge sort? Because it's actually pretty interesting how that works. Any objection? I'll put it this way. Any objection of demonstrating how merge sort works? Okay, so we'll do the worst case, okay? We'll try to throw something that is the worst case at merge sort, which means I give it something that is sorted in a reversed way, okay? So let's go ahead and do this. Mouse pad. Oh, I do not want to restore. All right, so we're going to give ourselves a, let me count. There are 15 numbers, okay? 15, 14, 13, 12, 11, 10. I'm just trying to debate whether I want to work with this many numbers or not. Maybe not. Maybe we'll just have 7 numbers. 7, 6, 5, 4, 3, 2, 1. So we got 7 numbers. And I'm using the mainframe, tape-based merge sort algorithm. So this one is not a recursive call. We basically just say we split this into 2 outputs. So whenever we see a run, we go to one single output. We see another run, the starting point of another run, we put it into the other output. So what this is going to do is this will get split into 2 outputs. 7, 5, 3, 1 is going to be one output, and then the second output is going to be 6, 4, and 2. Is that okay? Because what the algorithm is going to do is it is scanning the input and it asks, is the next item, it look at 7 first, because 7 is the first item of the entire series, so it cannot make a decision yet. But the moment it sees the 6, it's asking, is 6 continuing what I would call a run, which is an item, a fragment that is sorted. I want the array to be sorted in a non-decreasing way. So 7 and then followed by 6 means nope, we have broken a run already. So 7 by itself is one run. It goes to one single output. 6 is the beginning of another run. So we look at 6 and then we compare that to the next item. We broke that run again, okay? Because 5 is not at least 6. So 6 goes to the other output, and then 5 goes to the first output, 4 goes to the other output, 3 goes to the first output, 2 goes to the other output, and then 1 goes to the first output. Is that okay? So it looks like we're making the problem even worse. It's like, isn't this even worse than the original? Because 7, 5, 3, 1, they're spaced out by 2 instead of being spaced out by 1 in the original run. So now the question is, what do we do when we merge? So the way we merge is we look at the first item on both outputs first. And then we decide what is the best way to pick one of the 2 inputs so that we maintain the run as much as possible. So that means the sorting algorithm would look at the 7, which is the first input, the first part of the input, and then it looks at the 6. And then it will try to make a decision to say, I want to make a decision so that I can maximize a run when I combine the two inputs into one single output. So what would be the best way to do this? We want the output to be sorted in a non-decreasing way. So which one do you think do I want to use as the output to the to serve as the output value between the 6 and the 7? 6, very good. So we choose the 6 as the output. So now we are looking at the 7 versus the 4. So which one should I choose to continue the run as much as I can? I cannot use 4 because 4 is going to break the run, but 7 would continue the run. A run is basically a fragment of values that are sorted within that fragment. So I would choose 7 in this case. So after I have used the 7, then the 5 becomes the cursor of the first input, and at this time 4 is the cursor of the second input. So between the 4 and the 5, which one should I use? Both will break this existing run, right? So knowing that I'm going to break this run anyway, which one should I choose? The smaller value. Okay, you always choose the smaller value because the chances of being able to continue that run is going to be higher. So this time we have 4 and 5, and once we have 4 or 5 done, we have 3 in the first input and 2 in the second input. So we're going to choose the 2, and then the 3, and then the 1 of the last item. It doesn't have anything else to do, okay, because that's just a leftover after we have chosen all of the values. Is that okay? So now we split again. So when we split, we're basically saying, okay, we'll try to make a run as much as possible, stash it into one output. When it has a break, then we'll put the next run into the second output, and then we basically just flip-flop between the two outputs as we see alternating runs. Okay. So in this case, the first run is 6, 7. It goes to the first. It goes to the first output, and then we have 4, 5, as the second run going to the second output, and then we have 2, 3 as a run going to the first output, and then we have a leftover 1 going to the second output. Is that okay? All right. So now it's time to merge again. Okay, that's why we call this the merge sort method, because it splits and then it merges. So when we merge, the first item that we are looking at is the 6 of the first input and the 4 of the second input. So which one should I choose? The smaller one, right, which is the 4. So once I have the 4, now we have the 5 of the second input versus the 6 of the first input. I would choose the 5 because 5 is the smaller one. And now we have the 1 of the second input versus the 6 of the first input. We're going to choose the 6 from the first input. And then we have the 7 versus the 1. We'll choose the 7. And now we have the 2 of the first input and the 1 of the second input. Either one is going to break the run, right? Because 7 is the largest value of the entire series. So if I pick 1, it's going to break the run. If I pick 2, it's going to break the run too. So I'm going to pick the smaller one, which is the 1. And once the 1 is gone, then the second input has nothing else now, right? So I just have to dump the rest of the first input to this output file. So we have 2, 3 over here. So now we split again. So when we split again, we look at, that is nice. 4, 5, 6, 7 is one run. 1, 2, 3 is the other run. We only got 2 runs left. So now when we merge again, we look at the first item of each input. We have a 4 on one, a 1 on the other one. We choose the 1, right? The smaller one of the 2. And then we have the 2 versus the 4, 2. Then we have the 3 versus the 4, 3. And then The second input is now exhausted. So all we can do at this point is to dump what is left over of the first input, which are the 4, 5, 6, 7, and we're done. So we just have to split merge 3 times to get it sorted. Does that is that working out for you guys? The beauty of this approach versus the recursive version of merge sort is this works exceptionally well with tapes. The reason why it works exceptionally well with tapes is when we are splitting, the input is just read sequentially. We're just reading the input tape in a sequential way, and the way we output to the output tapes is also sequential. When we merge, it is also sequential because we are reading the input tape when we're merging sequentially, and then we're also reading the other input sequentially. The output is also sequential. So that means all of the operations, when we split, we are reading sequentially, we are writing sequentially. When we are merging, we are also reading sequentially and writing sequentially. So what is the big deal of being sequential? Why do we like things that are sequential?
Less operations to do.
We don't have to go back and forth, right? And going back and forth with a tape is not efficient. A tape is not a suitable medium for um, random access. So how do we know that? How many of you are old enough, or at least know someone else who's old enough to have to deal with VHS tape? Okay, so with VHS tape, I'm pretty sure you have siblings or someone else or yourself who like a particular segment of, let's say, a Barney tape. Yeah. So what do? Well, some of the VHS tape actually has a program to say repeat setup A, setup B as a time frame, and it can once you get to B, it will rewind back to A and play the whole thing again. It takes some time, doesn't it, to go back and forth because a tape is a sequential kind of device. So if you want to go from one point to another point, there's no way to jump to the other point. You really have to go through everything in between to get to point B. But random access is kind of like a hard drive. A hard drive is not entirely random access because the seek time and also the rotational delay, that's actually sequential. But it's fast enough compared to tape at least that we'll say, yeah, we call that kind of random access close enough. Why? Because the seek time is about 8 milliseconds or so, and it goes from the innermost track to the outermost track within that much time. Rotational delay is also even shorter, so we just kind of go like, yeah, it's kind of random access. But these days we have SSDs, solid state drives. That is, random access. So with all of these devices that are random access, why is tech still kind of obsessing over the thing about sequential access? What would be the purpose? Because if you put anything in the cloud, it is more likely that it's going to be stored in some kind of array of SSDs than anything else. It's not going to be on the tape. So why do you think I'm still kind of obsessed about accessing items in a sequential way? The funny thing, this is really funny. The funny thing is it is about RAM. Okay, you guys go like RAM? Isn't that very name RAM mean it is random access memory and it's not sequential? Yeah, I know what RAM stands for. Okay, I know RAM is random access memory. So what does that have anything to do with sequential access? Okay, I'll let you guys think about this for a little bit, and then I'll give you the answer. Hmm? It has to do with DDR technology. So what is DDR? I hope at least some of you are still kind of putting computers together or at least upgrading computers occasionally. What is DDR? Dubious doctor. The first D is dubious and then DR doctor, dubious doctor. No. DDR stands for double data rate. Okay? So we have DDR2, DDR3, DDR4, DDR5, and so on. So what is the whole thing about double data rate? How is it accomplished? And what does thing look like before we had DDR technology? So we kind of have to go a little bit low level. In order to access a particular location in RAM, there's a lot of overhead. Okay, you have to have the CPU has to communicate with the memory module and say, I need to access this thing at this location, and this is a read operation. That takes a long time. Okay, how long are we talking about? A lot of wait states. If you have set up a computer before and you're trying to squeeze the last ounce of performance out of a computer, you'll be looking at the wait states. You're trying to shave one or two wait states out of the read cycle, the write cycle, and so on and so forth. We actually have to introduce wait states, which basically means, hey, the CPU will basically say, this is the location, I want a read operation, and then it will say, RAM, you have 14 clocks to complete this operation. And meanwhile, the processor is doing this, twiddling its thumbs, waiting for 14 cycles to be done in order to get the answer. Because it takes that long for RAM to address the right location and get the content of that location onto the data bus. It's a very slow operation. So with a typical program, you'll be executing the next instruction, right? What do you think is going to happen again? The same thing, okay? The processor has to specify the full address, and you go like, out of those 64 bits of the address, we're only changing 2 of those bits. Yes, we are only changing 2 of those bits, but you're going to redo the whole thing, okay? We're going to access this location, give it all 64 bit of the address, specify the read operation, and then what? Wait for 14 cycles in order for that thing to come back. So what is DDR? DDR is a way for the processor to talk to RAM in a much faster way. What are we talking about? The processor will say, I want to start reading at this location, all 64 bits of the address, okay? Send it out to the RAM module. But then the processor will also say it's a read operation, but it's understood between the processor and the RAM that I'm not just reading one location. I want the location that I just specified and the next 64, 16, 32 location. Okay, that depends on the technology. So this time you set up the whole thing once. And then after that, RAM will basically, after the first initial wait of the 14 cycles, then RAM is just gonna pump back the additional locations without that setup time anymore. So you set up something which takes a lot of time, and then RAM will just clock back items every. I think if it's double data rate, then every time you have a rising edge of the memory clock, it gives you an item. Every time you have a falling edge, it gives you an additional item. So that way you save a lot of time. But then the question is, where am I going to stash all these bytes coming back? I just asked for 1 byte, and it's giving me 256 bytes. What am I going to do with the rest? What do you think? The cache, okay? But when you guys try to spec out a computer, most of the time you want to look at what? The level 3 cache, right? So as it turns out, the cache and DDR are tightly coupled. When DDR comes back with a chunk of memory, that lives in the cache. So what the cache is going to do is when the processor says, I need the next byte, the cache is going to intervene and go like, wait, hold on a second. We don't need to ask memory yet. Let me see if I have it cached. If it has it cached, then the cycle is really short because the whole thing about caching is it takes very little amount of time in order to access the content that is already in the cache. Are we doing okay so far with this picture? So going back to merge sort, what does it have to do with merge sort? Your other sorting algorithms do not do sequential access. Quicksort is all over the place, man. And it gets even worse because you also have your recursive call, which means you're pushing and popping items from the stack. But in terms of the access to the items in the array, it's all over the place. So if your access to RAM is all over the place, what's happening to the DDR technology? Is it buying you anything? You're reading all 256 bytes in. You need like 4 of those bytes. The next access of quicksort says, guess what? We're going to access something that is not cached. And you go all the way out again, and then DDR comes back with a chunk of memory, of which you only use 4 bytes again. Merge sort is exactly the opposite. It will make use of all of those bytes that you've got back, all 256, and then it will ask for another 256, ask for another 256. So if you're really you're trying to squeeze performance out of your computer, I would guess that merge sort implemented in the correct way can outdo quicksort, can outdo heap sort, and basically all of the other sorting algorithms because it has a sequential access nature to it. So the really funny thing about this entire discussion is the whole idea of RAM is random access. But the way we boost performance of modern computers is throwing that sequential access thing back into the whole thing. Because when you break that sequential access pattern, it will incur cost. This also relates to compiler technology. I know this is not a compiler class, and we are almost at the end of the semester. But when you think about instruction execution, it branches, right? So you have a branch because you have a conditional statement, goes one way or the other. You have a loop, it goes back to the earlier point where it has to exit the loop. All of this can potentially break that chunk of memory that you have just read that is cached. So there are compiler techniques that can try to make it streamlined so that your execution goes in the sequential manner as much as possible. So that way you can also squeeze a little bit more performance out of your architecture. It's not like if you don't do that, your program is not going to work. It will still work because this entire mechanism that I just talked about, the DDR technology, the caching and whatnot, it's all transparent from the software perspective. You don't even need to know about these mechanisms. But the compiler, in order to maximize performance, it would be wise to try to not break the execution cycle. So any type of conditional branches will affect performance. And this is not a computer architecture class, so I'll only mention that word, but I'm not going to explain it. Most modern architectures are deeply pipelined. And as such, anytime you do a branch, you're breaking the pipelining, and as a result, performance will suffer. So that's the other reason why we want to keep instruction sequences to be as long as possible without any branches, because branching will break the pipeline. If you're going to UC Berkeley, I think this is one of the concepts they will definitely talk about in their computer architecture class. Cool stuff. All right, so we are definitely at the end of today's lecture. So next week, we're going to take a look at the exam from last semester. So we'll start practicing for the final exam. Any questions before we adjourn for the weekend? Yes, it is Wednesday, and yet I'm saying have a nice weekend. Yep, you too.